Hello, we are doing our presentation on the Turing completeness of following dominoes. I am Todd. We have Nico, Kevin, and Dylan. So overall, when we actually are going from computational models to what is actually running on hardware in our computers, we typically use circuits, and those represent very small logic gates. And that layer of abstraction, we're able to actually translate to the world of dominoes. So dominoes can be used to form a variety of these logic gates, such as on the left, we have the OR gate, in the middle, we have the XOR gate, and on the right, we have the AND gate. We're going to use these machines to execute computation and be able to show and represent Turing machines' execution in the same way that computers can, showing Turing completeness. So the only ones we actually are going to need are going to be AND and NOT, but we don't have a way of being able to build a NOT gate since we can't just have a line of dominoes start falling if it wasn't falling before halfway through the circuit. However, we can actually use the XOR gate. And so what we can do is we can have our input on the tape go from being just W to having a 1 at the front and then having 1 and then our input W. And what we can do then is we can take that from our input and we can tie that to one of a XOR gate wherever we need a NOT. And as long as we keep in mind the length of the circuit and the amount of dominoes that are from the start of your execution to wherever you actually need the gate, if you tie one end high, the input will always be the opposite of an output, because if you have 1 and 1 into a XOR gate, your output is 0. And then if you have a 0 and a 1, your output is 1. And so from that, we can start to approach the idea of functional completeness. And so the overall concept is that a set of Boolean functions is functionally complete if and only if a combination of functions in this set can produce any possible truth table with any number of inputs. So essentially allowing us to build a truth table for any possible problem that a Turing machine could ever see. For example, for 2 inputs, a functionally complete set can generate all 2 to the 4 or 16 possible outputs.
And then from this concept, we could go to the post-completeness theorem, where it says that a system of Boolean functions is functionally complete if and only if the system does not entirely belong to any of these sets of functions. And we have T0, which is 0 preserving functions. And then we have T of 1, which is 1 preserving functions. Then we have L, which is linear functions. And then we have M, which is monatomic functions, and then we have S, which is self-dual functions. This means that at least one function in the system must not be 0 preserving, one function must not be 1 preserving, and then this follows on for the rest of this set. And then how we could apply this to dominoes is that since we could form the AND and NOT gate, we could prove that the set of gates of AND and NOT is functionally complete, assuming post-theorem, and then prove post-theorem. Then we could translate any given function to dominoes as shown before of making gates. So now let's examine 5 sets of binary functions mentioned earlier, of which AND and NOT must have at least one member that is not in the set to be functionally complete per post-completeness criterion. Here we are just finding the 0 preserving functions. These are the functions where we only have zeros as the input and the output can only be 0. From our example, AND gates are 0 preserving, since zeros ANDed together will always produce 0, but NOT is not 0 preserving, since 0 will always give you a 1 under the NOT function. And then here we're defining the 1 preserving functions, which is very similar to 0 preserving functions. All the inputs must be 1, and the output must always only be 1. Likewise, AND always produces 1, given 1s as inputs, and NOT always produces 0, giving 1 as input.
Now we can discuss L, the set of linear functions. So a function L is linear if it satisfies one of 2 different conditions. The first condition is that for every 1 valued input of F, the sum of the inputs is odd. And for every 0 valued output of F, the sum of the inputs is even. The second condition that it could be is kind of the mirror of this, which is that for every 1 valued output of F, the sum of the inputs is even. And for every 0 valued output of F, the sum of the inputs is odd. If we examine the truth tables, we can see that NOT is a linear function and is not a linear function. Next, we have M, the set of monotone functions. A function F is monotone if switching from any input xi from 0 to 1 can only ever result in the output switching from 0 to 1 or from 0 to 0, and it never results in the output switching from 1 to 0. We can check monotonicity by constructing the Haas diagram for a given function, and we can then verify that all paths from the 0 input, which would be all zeros, to the 1 input, which would be all ones, is strictly increasing. So here you can see the Haas diagrams for the not function and the and function respectively. So if we examine the condition that we mentioned earlier of increasing output values, we can see that and is monotonic, but not is not monotonic. And finally, we have S, the set of self-dual functions. So S is pretty simply defined. Basically, a function is self-dual if f of x1, x2, et cetera, equals not f of not x1, not x2, et cetera, et cetera. Again, by examining truth tables, we can determine that the not function is self-dual, but the and function is not self-dual.
So just to summarize the last couple of slides, we can see that for every set of functions, either one of not or and happens to be in each of these, which is exactly what we need. So the post theorem proof outline. So how we might go about proving post theorem? Well, we'll use our favorite tool, induction. So we consider the system of the 5 sets of functions that we just mentioned earlier, where F1 is not 0 preserving, F2 is not 1 preserving, F3 is not linear, F4 is not monatomic, and F5 is not self-dual. And from this system, we can build all possible truth tables on 2 inputs. That's our base case. Then we can perform induction on this table and show that given a system that can generate all possible truth tables for n inputs, we can generate all possible truth tables for n plus 1 inputs. So functional completeness to Turing completeness. We have a given circuit that solves one particular problem, but that's just it. It solves that one problem. So how can we kind of get it in a way to solve just generally n problems of n size? Well, to do that, we would need a family of domino circuits. And that would be enough for Turing completeness, where each member of that family is going to be a configuration to solve one case of that problem on a specific input size. So kind of by using families of domino circuits, we can show that dominoes as a concept is Turing complete, given unlimited dominoes we can use to build these giant patterns. In terms of practicality in the real world, dominoes, while a fun and novel idea for building something computable, aren't necessarily the most space or time efficient. Here we have Matt Parker's 3-bit adder, which took over 10,000 dominoes and also over 1 minute and 45 seconds to perform one computation. It's worth noting that for any of these dominoes that we set up, we can only do the computation once before having to reset them all up again to perform a different computation, which is certainly a hassle.